Hello, a warm welcome to each of you from IonQ, and thank you for your interest in being an intern with us. My name is Nicole Barberis. I'm the technical director on our sales team, but before this, I was a quantum machine learning developer. My job is to collaborate with clients on choosing their quantum computing use cases. As an intern working with me, you'll not only do a lot of quantum computing work in Qiskit, but I'll also coach you on technical writing and business presentation skills. You'll be exposed to the sales experience at IonQ, and this is a great opportunity to get ready for a career in quantum computing. Now, let's talk about the skills required for this project. Knowledge of Qiskit, Python, Jupyter Notebooks, TensorFlow, and LaTeX. Knowledge of quantum computing. A desire to learn more about the trapped ion quantum computers we build at IonQ, and be a self-motivated learner. Now, as far as the project, I would like you to create 2 Jupyter Notebook demos using existing examples from our GitHub libraries. I would like you to add images and annotations so that a business client could understand the demo. Set up a Google Colab environment. I would like you to make a video recording of the demo while it is being executed on the hardware. And then finally, present the work to the IonQ team. I sure hope you find this interesting because I certainly do, and I would love to collaborate with you. Talk to you soon.
Okay, hi everybody. My name is Amit Bhattacharya, and I'm here with Dominic Widows from IonQ, and we're going to quickly talk through the project or hackathon challenge that we had in mind for you. I'm going to introduce myself first really quick. My name is Amit. I've been at IonQ for a little more than 3 months. I'm relatively new. I have a background in data science and machine learning, and my job at IonQ is to use all of our data and data science and machine learning principles to hopefully improve system performance.
And hi, I'm Dominic. I've been at IonQ for just over a year, and I've worked for a long time in machine learning, artificial intelligence, and language processing, a lot of high-dimensional vectors, and I work on figuring out which of those models we can build most effectively on quantum computers by now.
All right, so we have a short little presentation. We're going to talk really quickly about what we had in mind for this challenge. So if we go to the first slide, we'll quickly talk about vectors. So I think we all know what vectors are from like mathematics, but in the context of machine learning and data, there's lots of different applications for vectors. So some are in like information retrieval and in terms of comparing documents and terms. Other forms of vectors are in machine learning, which use whether single-dimensional vectors or multiple-dimensional vectors as your inputs to regression and classification problems. And then nowadays, all throughout artificial intelligence, especially in natural language processing and images, vectors are everywhere. It's kind of like the basic component of what goes on. And especially in cryptography, as we're comparing what vectors are near each other and how to solve these problems. So just a very, very quick introduction to vectors and one of the main tools that we use. One of the main tools we use is something called cosine similarity. So here you can see 2 vectors, A and B. They happen to be pointing in different directions. And regardless of how long they are, we use a measure called cosine similarity, meaning like the angle between them. And so 2 vectors can be very, very different in length, but as long as they're generally pointing in the same direction, we consider those 2 things to be similar. And there's a little bit of math behind that, but as we transition into quantum similarity, it becomes a little bit different.
So, enter quantum circuits. In that simple 2-dimensional example we saw on the previous slide, where we just have 2 vectors, A with coordinates x1, y1, and B with coordinates x2, y2, it's very easy to see for normalized vectors with unit length that these can be represented as just a cos theta 1, sine theta 1, and B is cos theta 2, sine theta 2. And it's easy to create a very small quantum program, quantum circuit with just 2 gates in it, the output of which corresponds to the cosine similarity, as in the proportion of ones rather than zeros you expect when you run this circuit several times and measure the output, gives you the cosine similarity. The first challenge we'd like to suggest to you is to verify this both mathematically and experimentally, just in 2 dimensions. But the hackathon challenge really is about larger dimensions, because 2 dimensions isn't really that interesting. We wouldn't be building quantum computers to use in machine learning just for comparing 2-dimensional vectors. It gets interesting when we compare much higher dimensional vectors that get to the scales that are actually intractable to scale up on classical computers. So standard dimensions really in machine learning are, say, in the hundreds. For fast text defaults to 100, BERT, a big language model, defaults to 768. So that leads to the question we'd like to pose as a hackathon challenge. How many dimensions can you compare on a quantum computer today? What kind of accuracies do you get? So more formally, in the challenge, the input will be pairs of random unit vectors A and B in n dimensions. Build a circuit that measures the cosine similarity between A and B. What's the largest number of dimensions for which the mean accuracy is bigger than, say, 95%? So we're interested in this problem. We're kind of working on ourselves, happy to discuss it, and we'll be really interested in whatever solutions you come up with.
Okay, great. So thanks a lot. Good luck.
Good luck.